Welcome to Lecture 6.3, Fourier Sine and Cosine Series. So this lecture is going to be all about symmetry. And I want to emphasize that a Fourier sine series and a Fourier cosine series, this is different than just a standard Fourier series. It's related though. Okay, so we need some important definitions here, although these are quite easy. A function is even if f of x equals f of negative x, and it's odd if f of x equals negative f of negative x. So examples of this, let's do the even one first. So here's an example of an even function, approximately that is. And so why is this even? Well, that's because if we take a point x naught, then this is f of x naught, this height here. And if you take negative x naught, that's approximately negative x naught, then you get the same thing. So in other words, it's symmetric about the y-axis. So it has the symmetry like an even polynomial does. No, not when I say even polynomial, I should say a monomial like x squared or x fourth or x to the sixth. So even is the same thing as saying symmetric about the y-axis. Now what is odd? You might guess an odd function is analogous to, or it has the same type of symmetry as like x cubed or x to the fifth or x. So here's an example. If this is an odd function, it has to look something like this. So if this is x naught, and this is, one up here is f of x naught, and f of negative x naught, so negative x naught is here, and that has to be, and these 2 points have to be negatives of each other. So f of x naught is negative f of this point. So we say that this is symmetric about the origin because if we draw the line y equals, well, one way to think of it is if you take a point here and you reflect it across the y-axis and then across the x-axis, so across the y-axis and across the x-axis, then you get the corresponding point on the graph. And another way to think about it is these 2 points, if you connect them, it always goes through the origin. So that's what we mean by symmetric about the origin. Take this point up here and connect it, and that's going to connect with the point down here. And this is the negative of that. So odd is the same thing as saying symmetric about the origin, or the x-axis and the y-axis. Okay, so why do we care about this? Here are some really useful things, and this all has to do with why, in the previous lecture, a lot of these integrals that we did, a lot of these Fourier coefficients were zero. Now, we would like to be able to predict that in advance so we don't have to compute those integrals. So if, so how do I want to start out? So if, how about this one? If f of x is even, then if we integrate f of x, we integrate this even function. I said negative pi. Let me make it more general. Negative L to L dx. Then that's the same thing as just integrating twice from 0 to L. In other words, the area under the curve from, so if I integrate about a symmetric axis, or sorry, a symmetric interval from negative something to positive something, then the area under the curve is just twice the area from 0 to L. And that makes sense, right? It's just by symmetry. And similarly, the second fact I want to say is that if f of x is odd, then this integral is, or dx, is 0. And again, that's by symmetry. I think maybe I've made this picture a little too complicated to see that. But let me just draw it over here. If I have some odd function and I'm integrating about some negative L to positive L, then just by symmetry, remember integrals, you keep track of sine to area, and these things are going to cancel themselves out. So that is a really useful fact, and that's really behind why all those integrals on the previous lecture happen to be 0. Okay, so more facts. This is easy to check. If f and g are even, then f of x times g of x is even. If f and g are odd, then f of x, g of x are odd. And if one of these is even and one is odd, so if f is even and g is odd, or vice versa, then f of x, g of x is, is odd, and I realize I think I said it right, I wrote it wrong. That should be even. So think of these as like exponents. So even functions, for example, let's write down some even functions. Things like 7, that's an even function. What else? X squared is an even function. X to the 4th minus 2 is an even function. Any polynomial that involves only even degree terms, so x to the 10th minus x to the 4th plus x squared minus 2, that's even if I put a 3 out there. All of these things have only even degree terms. Okay. So what else should I say? Let's give some more that are not polynomials. The absolute value of x, that's an even function. Again, just think of the graph. That graph it's symmetric about. Ooh, I didn't mean to actually draw that. I thought I had my laser pointer. Well, that's fine. I'll leave it like that. Absolute value of x. What else? How about cosine of x is an even function. I mean that's going to look like this. That's symmetric. Well, it's supposed to be symmetric about the x-axis. What else do I have out here? There is an even square wave. We can make an even square wave like that. Cosh, hyperbolic cosine of x, is an even function, and there's tons of them. Odd functions. So 2x is odd. X cubed is odd. X to the 5th minus 12x is odd. Sine of x is odd. Think of sine of x has this odd symmetry. That sawtooth wave that we saw in the last lecture, that's odd. We can come up with an odd square wave. We can do a square wave like this. That is odd. Hyperbolic sine of x is odd. What about neither? Not every function has to be even or odd. Things like x squared plus 1, x squared plus x is not even or odd. If you have mixed terms, x, that should be a comma, but let me just get rid of it and make a space. E to the x is not even or odd. And you can see just from the graph of that, it doesn't have any type of that symmetry. But also, if you look at the power series expansion, e to the x equals 1 plus x squared over 2 factorial plus x to the 3 over 3 factorial, etc. This has even and odd terms. So it's neither even nor odd. Okay, so now that we know what even and odd functions are, I want to talk about even and odd extensions. So suppose we have a function that's defined only on a little finite piece, 0 to pi. So it's going to look something like this. Suppose it looks like this. This is 0 to pi. This is f of x. So in a lot of applications, we need, in order to solve a differential equation, we need to write this function using sines and cosines. So to do that, we have to, well, it doesn't have a Fourier series yet. It's not periodic, so we have to make it periodic. And there's multiple ways we can do that. So here's one of them. It's called the periodic extension. It's what we did, studied Laplace transforms of periodic functions. So it's pretty naive. We just take the thing and we copy paste it and we just make it periodic. And so forth. So this is pi, this is 2 pi, etc. This is the periodic extension. Okay, what else can we do? So sometimes we're going to have this function and we have to write it using cosine waves. And I haven't actually said this, but it's believable, and I'll justify it on the next slide, is that if we have an even function, its Fourier, even periodic function, its Fourier series will have only cosine waves in it. And if we have an odd function, then its Fourier series will have only sine waves in it. And we've seen that before, because the functions that we saw from the previous lecture were the odd square wave and the odd sawtooth wave, and those both only had sine waves in them. So now believe me, and then I'll show you that later, why that works. So now let's take our function. So what is the even extension? The first thing to do is to make it into an even function. So we are forcing this thing. So I'm taking this piece, I'm reflecting it across the y-axis, and I'm forcing it to be even. So now it's defined from negative pi to pi. And now let's repeat that thing. Oh, I didn't mean to actually draw that. And now let's repeat this thing. And let's do that again. That is the even extension. And finally, we have the odd extension. So sometimes we need to write this thing using only sine waves, because that's what we have. In that case, we take this function, and so we have to make it into an odd function. So let's reflect it across the origin. So from negative pi to pi, and let's make it odd. And so forth. So this is the odd extension. So 3 very natural ways to make a function periodic. This thing is going to have sine and cosine waves in its Fourier series. This is only going to have cosine waves, and this is only going to have sine functions in its Fourier series. Okay, so let me actually justify that now. So here's a key point. If f of x is even, then f of x times cosine of nx is even, because we have an even function times an even function. And what that means is that in the Fourier series an, we just have to integrate, instead of going from negative pi to pi, we can go from 0 to pi, and we can double it. So we put a 2 up here of f of x cosine of nx dx. And then similarly, f of x times sine of nx is going to be odd, because now we have a even function times an odd function, and therefore bn is going to be 0. And this is for all n. So for an even function, all of the an's, we have a simpler formula for this. We only have to integrate halfway, which is very nice if our function is discontinuous, like this square wave was. And then the odd ones, the bn's, are going to be 0. Okay? So the next point is, you can guess what's coming next. If f of x is odd, then in that case, f of x times cosine of nx is also going to be odd, because we have an odd function times an even function, which is odd. If you ever forget like what times a what is even or odd, think of it with polynomials. An even function is like x squared times an odd function is like x cubed. That's x to the fifth. That's odd. It's the same thing. Exponents add. So because of that, since this is odd, that means the, oh, I almost wrote it wrong, an, which is, an is 0. And if, similarly, f of x times sine of nx is even, because now this is an odd function times an odd function, and so that means that bn is 2 over pi from 0 to pi f of x sine of nx dx. So again, we are only integrating half of this, and we are doubling it right here. And it does make sense that, think about if you have a function like, like this one up here, which is a sawtooth. This looks like a sine wave. It really does. This thing looks like a sine wave, and so it makes sense that functions that have this type of symmetry, the same type of symmetry of a sine wave about the origin, that it's not going to have any cosine term. It's not going to have anything that has this. Any cosine of nx is going to have this type of even symmetry. So none of these functions can be any part of these functions right here. So now is one of the most important definitions in the chapter, or in the lecture, I should say, not the chapter. If f of x is a function defined on 0 to pi, then the Fourier cosine series of f is the Fourier series of the even extension, and the Fourier sine series of f is the Fourier series of the odd extension. This is important. If I give you a function with a finite domain, it does not make sense to say compute the Fourier series, because it's not periodic. And similarly, if I give you an arbitrary periodic function that already is periodic, it doesn't make sense to say compute the Fourier cosine series, because it is periodic. You might have more than cosines in that series. So, okay, so again, if we have a function, something like this, in the Fourier cosine series, what we do is we make that periodic. We make it even, and then we make it periodic. So I always think of it as 2 steps. Fourier cosine series, make it even, make it periodic, etc. And then we get that an, in a Fourier cosine series, an is 2 over L, 0 to, let's do pi. 2 to pi, 0 to pi, f of x cosine of nx, and bn equals 0. You don't even have to compute it. So in the Fourier sine series of this function, again, what we do is we take the function, and we make it odd, and then we make that, no, I didn't draw that very well, and then we make that periodic. Oh, I'm not very good at drawing this. I'm sorry about that. There we go. And so automatically, an is equal to 0. We don't even have to compute that. And bn is 2 over pi, negative, or 0 to pi, f of x sine of x dx. And, I forgot my dx up here. So you can use these formulas right away. And there are analogs for this when it's L periodic rather than when it is 0 to L instead of 0 to pi, but it just makes it messier, and I think you learn the same amount by studying, by just fixing this to be pi. Okay, so I don't think there's anything else I wanted to say about that. I think that's it. So a common mistake I see is when I say compute, again, there's a difference between compute the Fourier series of f of x versus compute the Fourier sine series of f of x. I cannot ask both of these about the same function. This function here has to be periodic. And if I want to ask you to compute the Fourier sine series, or the Fourier series, and if I want you to compute the Fourier sine series, this thing better be defined on a finite interval, like 0 to L. Okay, so let's do an example. Here's the function. F of x equals x, defined on 0 to pi. This is f of x. And we need to compute the Fourier sine series and the Fourier cosine series. So the Fourier sine series, let's do that one first. So we often just call it the sine series. So we take the function and we make it odd, and then we make that periodic. And notice that this is something that we've seen before. In the previous lecture, I think it was example 2, we computed the Fourier series of this exact function. So I don't need to do it again. I'm just going to say this is example 2 from the previous lecture. I think it was example 2. And what we got was that f of x equals n equals 1 to infinity of, we didn't have a closed formula for, oh, yeah we did. We had, it was negative 1 to the n times 2 over n. Actually, it's negative 2 to the n, so yeah, there has to be a negative sign here. I can put that, I'll just put that there. Actually, you know what's better? Instead of putting that there, I'm just going to make this n plus 1. Same thing. Times sine of nx. Okay, so that's the Fourier sine series. Let's do the cosine series. So this thing, we take the function now, right here, and we need to do two things. We need to first make it even. There we go. And then make that periodic. And so we see that we get this triangle wave type thing. Okay, so the Fourier cosine series is going to be f of x equals, oops, let me put in my constant term, a naught over 2 plus n equals 1 to infinity of an cosine of nx. And we got to figure out what a naught is and what an is. So let's do a naught first. So a naught is 2 over pi times 0 to pi times x dx. And I claim that without even doing this integral, I know what it is. And let me show you why. So this a naught over 2, I claim this thing is always the average value of f of x, just of the function. Now in Calc 2 you learn formulas for how to compute the average value, and you don't need to know that for this. This is the formula. This tells you how to do it, well, by a factor of 2, because of that 2 there. But all you need to know is that you don't need to know this, but very frequently you can just spot the absolute, or the average value by inspection. Like, it's very clear that the average value of this function is pi over 2. Now let me write that out. So the average value of this function is pi over 2. And that should be obvious why that is. It just goes right through here. And let me justify why this is the average value. So let's suppose you had a periodic function that had no constant term. It had just sine waves and cosine waves. Then I claim that that function is always going to have an average value of 0. I don't know what it's going to look like, but any sine and cosine wave is going to have an average value of 0. So no matter how you add them up together, you still get a function with an average value of 0, whether or not it's periodic. So for example, some weird function like, let me redo that. So some function Oh, I'm not going to be able to draw one average value of 0. Yeah, let me not just try. But if the average value of 0 has 0, then it better be just sines and cosines. Because now if we have a function like this, or this, where the average value is clearly pi over 2, then it can't just be sines and cosines. You have to start with sines and cosines, but then to move this function up to pi over 2, you have to add a constant term. This thing is just a vertical shift. Adding a constant just shifts this thing up by whatever constant that is. So if your average value goes from 0 to pi over 2, then this thing better be pi over 2. So in other words, for this example, a naught has to be pi. Careful, a naught over 2 is pi over 2. Okay, so it's very common to think a naught is the y-intercept. That is not the case. A naught, that's a common misunderstanding. But a naught over 2 does have meaning. It's the average value. Okay, next. Let's find the ANs. So AN is 2 over pi, 0 to pi, times f of x, which is just x, times cosine of nx. And again, I don't need to integrate. There's a quarter here. I would normally have to integrate two little pieces, but because we're only going from 0 to pi, we don't have to worry about that. And I just realized, I labeled my pi wrong. This is actually, that should be 2 pi, right? Yeah, pi is there. So that should be pi. Okay, and that is negative pi. Sorry about that. Okay, so this thing here is, so let's do integration by parts. Let's let u equal x. I'll do this quickly because you should be experts at this by now. Du is dx, dv is cosine of nx, dx, and I forgot my dx here. I'll turn that into a dx. And v is 1 over n sine of nx. So this thing here is 2 over pi times u times v, which is x over n sine of nx from 0 to pi. Hey, look at that. That's going to be 0 because we know that sine of n pi is 0 and sine of 0 is 0, so we can ignore that term. And then minus the integral of v du. So that's this times this. So that is going to be 1 over n sine of nx dx. Okay. So this thing here is going to be 2 over pi times, so the integral of sine is negative cosine, so we're going to get 1 over n squared times cosine of nx from 0 to pi, which is 2 over n squared pi times cosine of n pi minus cosine of 0, which is 1. That thing is 2 over n squared pi times negative 1 to the n. Remember? You should always, that should be a knee-jerk reaction. When you see that, that's negative 1 to the n. Minus 1. And this thing is, what is this? This is negative 4 over n squared pi if n is odd. Is that correct? If this is odd, then we have negative 1 minus 1. And if it's even, this becomes 1 minus 1. So we have 0 if n is even. So in other words, we now have our Fourier series, f of x equals pi over 2 plus n equals 1 to infinity of 2 times 2 over n squared pi negative 1 to the n minus 1 times cosine of nx. And notice that this function, this is actually exactly point for point this term. We don't have any discontinuities here, because up here we technically, remember, like at this breakpoints, this function actually equals 0. This is exactly that function point for point. Now let me just check to make sure that we did the right thing. Why are these things negative? This function looks positive, right? It's above, this looks like a polynomial that's concave, it's positive. Does this make sense? I claim it does. Okay, so what does a cosine wave look like? A cosine wave looks like that. I'm not going to draw this very well. It's concave down like that. This is concave up. So this is like a cosine wave upside down, like a negative cosine wave. So it makes sense that if this thing is concave up like that, it's going to consist of not these things. So this is like cosine of nx. Cosine of negative nx is going to be something like that. And so it's a bunch of these things, and of course, look at that. That's got to get shifted upwards by pi over 2. So this perfectly makes sense. Okay, so here's an example. Let's compute the Fourier sine and cosine series of this function right here. So let's draw a picture of that. Oh, get my pen back. So this function looks like this. This is pi. This is pi over 2. And so the Fourier sine series, we got to do two things. We take this function, we make it odd, and then we make it periodic. So this is pi over 2, and this is pi. And then the Fourier cosine series, we take this function and we make it even, and then we make that periodic. This is pi, and this is pi over 2. So I'm actually only going to do one of these two things. I think I'm only going to compute the Fourier sine series. I'm not going to do the cosine series, but I will get you started on this by drawing it like this. And I encourage you to, after this lecture, do this yourself. It's going to be analogous to the sine series. You're going to use similar symmetry arguments and tricks, which are very good practice. So make sure that you can do it after. Okay, so let's do the sine series. So how do I want to start this? Let's see. So here's what I want to do. I want to draw this a little bit bigger. And I want you to notice that this symmetry about, so we're only focusing from 0 to pi. This is our world. It's right here. It's this little window. This function is odd, but I'm only looking at this window, and I want you to notice that the symmetry about this, so this is pi over 2, that this thing has, I'm going to say in quotes, even symmetry about the line x equals pi over 2. It's an odd function, but if we focus on this line, it has even symmetry about that line. And now I want to compare that to the symmetry about some cosine waves. So I'm going to draw 4 cosine waves, and I'm going to draw pi. So maybe I can fix that. Let's make that a little bit more out there. Pi. So I'm going to draw sine of x, sine of 2x, sine of 3x, and sine of 4x. So sine of x looks like that, about. It's going to be a rough sketch. Sine of 2x is going to be like that. Sine of 3x is going to be that, and sine of 4x is going to look like that. Oh no, that's not right at all. It's tricky to draw these things. I had to erase some of my axis. Okay, so sine of 4x is something like that. Okay, and now notice the symmetry about this line, this vertical line. So which of these functions have the same type of even symmetry about this line as this one? Well, clearly that one does, and that one does. And these things do not. So for the same reason why odd functions only have sine waves in them, because they have the same type of symmetry, this type of odd function is only going to have the same type of sine waves, these guys, as it's going to only have the same type of sine waves that match the symmetry. So these functions are even symmetry, and then these functions here have odd symmetry about that line. So the Fourier sine series of this thing or of this function, is not going to have any sine of 2x terms, sine of 4x terms, even sine waves. I don't even sine of nx for even n. And if you may remember, in some previous examples that we did, a lot of the coefficients, we got like 1 minus -1 at the end, so all of the even terms were 0, or all of the odd terms were 0, things like that. And there's always a reason like this behind the scenes. Okay, so our conclusion is that if n is even, then Bn is equal to 0. And moreover, if n is odd, well then Bn is 2 over pi from 0 to pi x cosine, not cosine, I'm sorry, sine. Oh, I should also be careful here. It's not x, it's f of x, sine of nx dx. And this is not a differentiable function. So this is x pi minus x. So I normally would have to break this into two pieces. So I'd normally have to say that this is 2 over pi, 0 to pi, x sine of nx dx plus 2 over pi, 0 to pi, pi minus x, sine of nx dx. And that's not fun to do this thing twice, and especially this thing. Okay, so what we're going to do instead is that we're going to use the same argument that we did for even and odd functions. Instead of integrating from here to here, I'm going to integrate from here to here and double it. Because if I multiply one of these functions times one of these functions, I'm going to also get, both of these things are even about this line, so the product will be even. So in other words, I'm going to write this as 4 over pi from 0 to pi over 2 times x times sine of nx dx. So I'm going to integrate only halfway, and I'm going to double it. I cannot always do this, but I'm being clever. I'm critically thinking here to save myself some time. Okay, so let's integrate by parts now. This is u equals x d, not, is this by parts? It's, yeah. I always forget the names. I know how to do them though. Du equals dx. Dv equals sine of nx dx, and v equals 1 over n cosine of nx, and I need to put a negative sign there. So, okay, so this thing here, this is 4 over pi times u times v, so that's negative x over n cosine of nx from 0 to pi over 2. And notice that if you plug in 0, this x makes it go to 0, and pi over 2, cosine of pi over 2 is 0. Here's a unit circle because that's the x value up there. So this whole thing is 0. We don't have to worry about that. And then minus u integral v du. So that's negative 1 over n. Let's absorb that negative sign into here. Cosine of nx dx from 0 to pi over 2. So this thing here, okay, so now we have 4 over pi. This integral is 1 over n squared sine of nx. And do I have to take a negative sign? No, I do not. And that is that correct? Did I do that right? Yes. So we got to go from 0 to pi over 2. So plugging in 0, that's going to give me 0. So this thing, the whole thing simplifies to, actually let me do it down here. This simplifies to 4 over n squared pi times sine of n pi over 2. So now what is this? So this is Bn. What is sine of n pi over 2? So here's the unit circle. Sine of n pi over 2, that's either here, 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 or here. So that's either, if it's here, it's 0. So the sine is the y value. So that's 0, 1, 0, or -1 if we're down here. So this thing here, if you wanted to, you can write this as 0 if n is a multiple of 4k. It is 4 over n squared pi. So this thing is positive 1 if n is up, if we're up here. So that's 1 more than a multiple of 4. So if n is 4k plus 1, it's 0 if n is 4k plus 2, and it's -4 over n squared pi if n is 4k. This is something you don't need to know how to do. I mean, it's perfectly fine, I think, to leave your answer like this, sine of n pi over 2. I think this is a simpler condition than this here. But it's worth saying what this is. So what this thing looks like, so let's write this out. So let's go up here, f of x. So what we have is we have all of the even terms, and actually this is what we wanted. All of these even terms are 0, because those don't contribute. So we only have odd terms, and they alternate in sign. So f of x equals 4 over pi times sine of x minus 4 over n squared, 9 pi times sine of 3x plus 4 over 25 pi sine of 5x minus 4 over 49 pi sine of 7x plus minus. This is what, so this infinite sum is precisely this function here. And this function, if we extend it, you can see it's this triangle wave. And because it's continuous, we don't have to worry about that gap issue, discontinuity issue. So this function converges exactly to this even extension. So this is the Fourier sine series of this function here. Okay, so here's the last example. This is something that we are going to use a lot in section 7 in a lot of different lectures when we do PDEs. We are going to have this function, and we want to compute the Fourier sine series of this function. So to do this, well, let's sketch it first. So this function looks like, well, I'm going to move it down here. So this function is a parabola. This is pi. This is 0, and so it's a parabola that looks like this. But we're only going from 0 to pi, and so the Fourier sine series, we first make it odd, and then we make that periodic. So it sort of looks like a sine wave, but it's not, because these things are actually parabolas. Okay, so let's do this. So Bn is 2 over pi, 0 to pi, of x pi minus x times sine of nx dx. Now this is a nasty integral. You have to integrate by parts twice. You let u be this. I don't want any of you to do this by hand. If I give you a problem that's this complicated, please use a computer. I mean, I do. It's just not worth your time. If you were to do it, you'd probably make a mistake, as would I, and then we'd get the wrong answer. And yeah, so I just went to Wolfram Alpha, like right before recording this lecture, and I have it in front of me. And what Wolfram Alpha says is that the integral, I literally type it. This is a great tool. It can solve almost any differential equation that has a closed form solution. Maybe I shouldn't be telling you this, although by now we've done all the homework for solving differential equations, just about. So Wolfram Alpha, I type this in and I hit enter, and here's what it gives me. It gives me n squared x. This is unbelievable. X minus pi, and it knows that what's a variable, what's a constant, times cosine of nx plus n pi minus 2x times sine of nx. Okay, so, oh, I forgot, all over n cubed. So please don't do this by hand. Don't. So what are we doing? What we have to do is we got to integrate from 0 to pi and times 2 over pi. So let's divide this thing by pi. Put a pi down here. Let's put a 2 on top. Let's stick a 2 here. Let's stick a 2 here. And then let's go from 0 to pi. Now you could put in the definite integral, but you know it's not going to simplify the way you want it. It's really not. Trust me on this. And it's just as much. I claim it's even less work to do it this way, to do the definite integral and then to plug in 0 and pi. And let me show you why. So let's plug in. Let's look at these terms. So this whole term here, this is going to go away. When we plug in pi, x minus pi, that is 0. And when we plug in 0, n squared x is 0. So this entire term right here goes to 0. Isn't that cool? So what else can we say? Look at this sine of nx term. Sine of nx, that is going to be, that sine of n pi, if we plug in pi, that is 0. And sine of 0 is 0. So this entire term, what's connected, this whole thing here is going to be 0 as well. So right away, we've reduced this thing greatly to, what is this, negative 4 cosine of nx over pi n cubed from 0 to pi. And I mean, look at that. So we have negative 4 over pi n cubed times cosine of nx, n pi, minus, and Wolfram alpha is going to leave your answer in terms of cosine of n pi's and sine of n pi's, which are not as simple as you want. So trust me, just use the indefinite integral for these and then plug in. Okay, so let's move this negative sign inside here, and let's write this as 4 over pi n cubed times 1 minus negative 1 to the n. And there we go. That's our bn. We are done. So this function here, f of x, is n equals 1 to infinity of 4 times 1 minus negative 1 to the n, oh, I forgot my n parentheses, over pi n cubed times sine of nx. This function, with the help of Wolfram alpha, it only took me a couple minutes to do. It was pretty easy. And this is exactly the function right here. And this is going to be super helpful when we study PDEs in the next series of lectures.